Welcome to Breadboarding. In the previous video we managed to get the floppy disk controller up here booting MS-DOS 3.3.0 and MS-DOS 5, and at the end of the video I talked about what we're going to be doing during this video, which is looking at installing an 8 and 16-bit compatible VGA video card and install this, hook it up to the Breadboard PC. So this is video 21 in the Breadboard PC 8088 version 2. And in our high-level plan, where we completed our basic Nanocomp 8088 with an LED display keypad, we've got the basic floppy disk PC with the CGA video controller booting MS-DOS or floppy disk. And in this third phase, what we're going to be doing then is installing the VGA video card. We're later then going to be looking at adding a disk controller, booting MS-DOS from the hard disk, installing a mouse and getting a mouse running, and then installing and running Windows 1, 2 and 3. So earlier in the Breadboard PC series we covered what makes a micro IBM PC compatible, and the things in green we've already covered, so I'm not going to go through those. The things down in red at the bottom we've just finished with, so we did the floppy disk controller without using direct memory access, DMA, and we used programmed I/O. But one of the things that we hadn't done yet is the PC had an ISA or industry standard architecture 8-bit or 16-bit expansion bus, or known as the system expansion bus in some documentation. And so what we're going to be doing in this video is we're going to be installing an ISA slot, plugging it into the rest of the Breadboard PC and seeing if we can get the VGA video card to start up properly and work with the BIOS. And this second slide here shows where we're taking components and functions from various generations of PC. The IBM PS2 range is actually where the VGA video controller was introduced. Obviously the CGA graphics controller is what was made available with the first IBM PC and PCXT, and you can see that we've added for the PC80 the real-time clock, the standard post port and dual interrupt controllers. So the Breadboard PC contains features that spread across these various hardware generations. Now VGA video is now pretty much the bare minimum standard and has been the case probably for the best part of 30 years now. This is from the VGA documentation and shows the various PC video modes. Now what I've done here is highlighted the CGA modes in yellow, the EGA modes in orange. So this is kind of intermediate between the CGA and the VGA video standard. CGA and EGA required dedicated digital monitors, so these had digital TTL inputs to the monitor red, green, blue controls, whereas VGA has analog inputs to the red, green, blue voltages and so can do almost an infinite number of different colours. And the monochrome display adapter, which we did in the first series, would only output to the black and white or green or orange display and tended to work at a slightly different resolution. Now the VGA video controller is actually able to reproduce all of these modes, although we'll be dealing with a VGA compatible output monitor. Why are we actually bothering with a card rather than trying to make one of these things? Well, because the VGA card is actually compatible with all these various video standards, you can't actually have the monochrome display adapter, CGA adapter, EGA adapter installed along with VGA, and because VGA does all of these, it makes it actually quite complicated. Now the chip we're going to be using is a Trident TVGA 9000 series chip, and this particular chip has 160 pins, and the VGA technical guide, just to give you this came from the original IBM PC documentation, is over 108 pages long. So this is a document that just describes how the VGA video card is managed and configured and has all the details at the high level design, all of the various configuration registers, memory maps, etc, etc, etc. So this is 108 pages. I think when I counted there's over 60 odd configuration registers. Now to try and produce this on breadboards is going to be too difficult. It might be possible with a field program or gate array or something like that, but really we're going to need to be soldering chips with 160 odd pins or more, so it's not really practical for doing on breadboards. So I took the decision to try and find an old second-hand VGA compatible video card. And just to give you an idea of the complexity of VGA over the earlier controllers, so these are the diagrams that have come out of that document. So this is the block diagram, the CRTC being the 6845 compatible cathode ray tube controller chip we were using. The video DAC is similar to the one that we were using earlier in the series, but a lot of this complexity here is all built in custom large-scale integration chips in the original IBM PC and in subsequent VGA compatible cards. Then there's the graphics controller block diagram, in particular the multiple banks of 64K of memory, so quite often 256K of memory as a minimum in 4 64K banks. The attribute controller is substantially more complicated, and various things to do with pixel panning and all sorts of things like that. Then there's all sorts of features that are able to do more complicated things to do with manipulating the data as it's being saved to the various banks. The ability for it actually to do some level of comparisons as well within the controller itself. And this is just the summary of the configuration registers. And you can see here that some of the register addresses are compatible with the monochrome display adapter. Then some others are then the CGA compatible configuration registers. And then these ones here are the EGA and VGA registers. And what I should say here is the attribute registers here, there's an address register and other attributes here. So the address register here allows even more registers for the attribute, the CRTC, sequencer, and the graphics registers. And for the CRTC, the original CGA MDA had, I think, about 16 configuration registers. So there's about another sort of 8 or 9 there. And then these other registers, this is where the general registers, sequence registers, attribute registers, these are all the other configuration registers which are accessed by an address and then the actual register data itself. So you can see there's an awful lot of configuration here, and to try and produce this on a breadboard was just not going to be practical. And then there's also the various way how the video memory is addressed. So these are all the various ways how it can configure the video RAM for being addressed and the way how it's multiplexed. So the complexity of VGA is an order of magnitude more than we had with the CGA. One of the interesting things in the document as well, it also shows, we've talked about previously, where the vertical sync and horizontal sync signals that go to the monitor were used to tell the monitors how many lines the display was made up of. So you can see here that depending on the positive and negative sync signals here, whether it's 480 lines, 350 lines or 400 lines. So this is the VGA video card we're going to be using. So it's the Trident 9000 series, happens to be a 9000C. Now I have got some documentation for an earlier version of this type of card, but it doesn't quite match it. What you can see here, we've got the main VGA controller chip here, which is the TVGA 9000C. Then there's the video DAC, and this also does the clock timing as well. You can see there's one 14.3 megahertz crystal here, and that's used by phase lock loops to actually produce all the different frequencies needed for the VGA resolutions. And in fact, this can do Super VGA as well, so you can go all the way up to 1024 by 768. And then this is the Trident Video BIOS. So this is a 32K ROM. This version happens to be C4.4, and we'll see why that's important in a minute. And you can see that the 32K Video BIOS is actually fitted at C0000 up to C8000, effectively 7FFF. We'll be looking at how the main PC BIOS actually finds the video BIOS in a minute. So this is upside down just because of the chip labels were this way around. And these two chips here seem to be 256K by 8 bits, 70 nanoseconds. So this is quite fast dynamic RAM. And this gives the board 512K of RAM. So then if we look at the card the natural way around, you can see here the chip labels and things are upside down here. And on here you can see that we've got a number of jumpers here. So I'm just going to go through and look at what those jumper meanings are. And I have got some documentation for an earlier version of this card. It doesn't completely match the board, but it's pretty close. Now, jumper 1 doesn't actually exist on this card. And in the earlier card for the documentation, this was to configure between 256K and 512K. What you can see here, we've actually got two 256K RAMs here, 70 nanosecond, I think. Can't find any data sheets for these particular ones, but it appears that they are 8 bits wide by 256K to allow the 512K that this card supports. So J1 doesn't exist on this, but when we look at the documentation, you'll see that earlier versions of cards, it was possible to upgrade from 256K to 512K. Then jumper 2 here, which is just here, is actually to switch between the interlaced video and non-interlaced video. Then jumper 3 is part of the configuration between the 8-bit mode and auto detect between 8-bit and 16-bit mode. So the connector down here, this is the 8-bit standard bus connector, and then this is the extension that was added from the PC80 onwards for 16 bits. So we're actually going to configure this to be dedicated 8-bit, so we don't actually have to worry about the 16-bit connector there. Then there's another jumper here which configures between 8-bit and 16-bit. Another one down here between 8-bit and 16-bit. The difference in colour is only because I couldn't really read the yellow when it was down the bottom here. And then these 3 jumpers again here need to be configured this way for 8-bit. With the card configured like this, we should be able to plug it into a socket and only have to worry about the 8-bit port signals here. And if we just have a look at the card, I'll just switch it over. You can see that in fact on the back, there's only a handful of the connector pins are actually connected on the back here. So there's only 3 on the 16-bit one, and there's a few more here, but we'll be going through all of the pins here and work out which ones we need to connect. There's not many on the back of the card there on the solder side, and there's a few gaps. I think there's might be 1 missing there and 2 missing there. So we'll need to actually have a look at that in a minute. So looking at the data sheets for those, so the Trident 9000C data sheet covers a lot of the information about it, and I've picked out a few highlights from it, but all the timings and the various video modes. So this chip is actually capable of doing output video frequencies for MDA, CGA and EGA, although obviously this will only be used actually for VGA output for monitors, but it was capable of doing the timings for different lower versions of the video standards. And this particular thing we'll look at in a sec, and this is the pinout in ISA bus mode. This chip could also do the IBM PS2 microchannel architecture outputs as well. And then the other chip here is the video digital analog converter, and it also is the clock synthesizer as well, so this can produce all the clock signals needed for the various video modes, all the various configuration registers and things here. So the documentation is available here. Hopefully we won't need to access this documentation, as the video BIOS should hopefully do everything that we need here. So this is the excerpts from the datasheet here. So you can see with the Trident TVGA 9000, then we just need to plug in the dynamic RAM. Now in this case, this is 256K times 4, and the fact that we have 256K times 8 means we only need 2 chips here. You can see we've got the BIOS 32K ROM here, the 8001 digital analog converter and clock controller, and then there's just our 15-pin VGA connection. So you can see here that the minimum configuration just requires the 9000C, the 8001, 2 dynamic RAMs, 32K EPROM, and the 14.3 MHz crystal and various jumpers, ferrite beads, capacitors, resistors. Should also say that Sergey Kiselev, whose XI8088 BIOS we're using here, has actually got a ISA Super VGA card, which is based on the Trident 9000 series chips. I could say this -0degrees.net has good background information on the video modes I was talking about there. In particular, the multicolour graphics array, which was kind of halfway between CGA and VGA. But this is Sergey's GitHub site with the ISA Super VGA card. You can see here it's actually using a slightly later version of the chip, I think, the TVGA 9000i. I think this also had the video DAC built into it as well. You can see here this is the EPROM and the video RAM here. So Sergey has done this, so I didn't see very much point in trying to reproduce this on breadboards, given that we'd need to have the sort of 160 pin type chip to actually do this. And it's also interesting here that there is one particular issue with the original IBM PC and PCXT in the way how the address latch enable timing during DMA would sometimes confuse this. So there are some changes you could make to this particular board. Fortunately, we're not using DMA, so this shouldn't be a problem for our particular card. But if you are trying to get the sort of VGA card working with older PCs, then you need to be aware of that issue. And sometimes you have to do sort of fixes like breaking the tracks and things, tying things to 5 volts to avoid the problems. And this also says that the chip here actually maps the video ROM here to C0000 to C7FFF. And so when we actually install this into the Breadboard PC, we should be able to use the built-in monitor on the LED display to set the segment to C000, and we should then be able to go through and have a look at the video ROM to see whether or not it is actually accessible. And what I was able to find is there is a site out there, I haven't got the URL directly to hand, but there is a site where the video BIOS is actually available. So this TVGA 9000C bin is actually the VGA BIOS dumped. It's a slightly later version card, so you see this is 4.5 rather than 4.4 from the same year, 1994. And if we actually look at this in hex mode, so we have the magic number here, 55AA. Then the next byte is actually the number of 512 byte blocks that the BIOS is. So 40 means it's 32K. And then there's also then the address offset where the code needs to execute from. So you can see that some of the early parts here are sort of strings and things and the copyright messages. And this also contains the VGA font information for doing in graphics modes. And also VGA actually had software definable character fonts. The BIOS would actually load the character information in the ROM here into the memory, which is used by the VGA card. And I've actually got one of the VGA fonts that we used earlier in the series. But you can see here, if you actually look at this second character here, it starts with 7E81A581. So if you actually to copy that and look in this file, you can actually find that the fonts actually are buried halfway in here. And if we actually go to the end of the font file here, you can see that we've got 7C, 7C, 7C. So if we just copy that and search in here, then we can see that we've actually got the font information embedded in here. So when if we wanted to disassemble this, then obviously we'd need to know where the various string tables and the font information is. You can see here, this is where the font information is in the video BIOS. So what I'm going to look at now is how does the BIOS actually search for where the extension ROMs are, and particularly for the video ROM. So in the XI8088 BIOS, the loading of the VGA Video BIOS, we're going to have a look at the code in a minute. But basically what the BIOS is doing is scanning from this address to this address, looking for this magic number. And it's looking in 2K increments, which is the standard in the original IBM PC. And when the magic number is found, it reads the size of the blocks from the second byte. So it's the third byte, byte 2. Calculates the total number of bytes. Then it reads through all the bytes and sums them all up and calculates a checksum. If the sum is not equal to 0, then it reads the next 2K chunk, so it means the checksum is not valid. If the sum is 0, then byte 3 contains the offset, the code to execute. It writes that offset and the segment, which is C000, to a section of the BIOS data area in these two particular addresses. Now in the XI8088 BIOS, these don't have a label particularly, so they're just 67 and 69. And then the BIOS does a far jump to the address in these two ranges here to run the video BIOS. And when the video BIOS returns, then it skips the built-in monochrome display adapter and CGA video BIOS initialization. So this is the output listing of the video BIOS, and I have got some bookmarks here. So So this is just some annotation I've added. So the BIOS extension address at 6.7 and 6.9 is in this BIOS data area, and you can see there's all sorts of other information here. But this is where the BIOS extension code actually puts the address to execute any of the ROMs that it finds. It can also be used for things like disk controllers and things like that. It might also have ROMs that it would detect and would execute the code in there. Then basically during the initialization period, it looks for a video BIOS. So we can see here that the host code that is output here is for the video BIOS scan. And we output that. You can see here that we're initializing the C000 and C800 is the range that are actually going to do the extension. We then call the extension scan. And what this does is searches for our magic byte in that range. It maintains a checksum here. If the checksum's not 0, then it goes to the next range. So it says, well, it's not valid, so you don't get anything logged here. If it is valid, then it puts the offset into 6.7, puts the segment in the 6.9, and then exits. And then once it's returned from here, it then says if the offset is 0, then we go to no video BIOS and we carry on doing the BIOS initialization for the monochrome display adapter and CGA adapter like we've been doing up till now. But if there is an offset address there, then it will then say we're initializing the video BIOS, sends it out to the power and self-test port, and then this call var to 6.7 hexadecimal will actually take the address and the code segment in the BIOS data area here and actually execute that. Once it returns, it will then set the data segment back to the BIOS data segment, and then we'll jump to video initialize. This is actually commented out in the XI8088 BIOS source. I need to check to see whether or not this needs to remain commented out or not. This is how the BIOS actually scans for the video BIOS, and what we should then see is it will output the power on self-test code. So even if the VGA adapter doesn't initialize correctly, we should at least see that it scanned it and found it. So now just going to take a look at the ISA Bus connectors. So this is an ISA Bus connector. There's two sides, A and B, C and D, so the 16-bit is at this end. And what I have done is soldered that onto a bit of strip board. Is then got a break all the way down there. We've got the pins to plug into the breadboard, and then also put labels on there, so it might be the brightness may not be right. They've then actually got the labels, so this is the B side from 1 to 31 there, and that is the A side. So that's primarily the data bus and the address bus and one or two other control signals there. So we're going to need to have a look at what those bus signals are and how that's documented. So this is the schematics from the original PCXT. At the end here, there were two sets of connectors. Now in the original PCXT, there was a specific socket 8, which had some special differences in the configuration, which we're not going to worry about. But you can see here that the connector here, we've got the D0 to D7, we've got A0 all the way down to A19, and then there's the various IO read, IO write, memory read, memory write, various clock and oscillator signals. A lot of these ones here, the DAC and DRQ, are all to do with DMA, so we don't need to worry about that. There's the active high reset signal. Address latch enabler is one that we will need to worry about. And you can see then that there's the IO check and IO ready, which are related to memory and IO timings and parity errors, the interrupts, and then some voltages. Now, generally we only need to worry about 5 volts, and the video card does appear to use 12 volts as well. So we're going to have to be careful hooking up 12 volts there, that we don't hook it up to the wrong connection, otherwise that might kill things. We're not going to need to worry about -12 and -5. So then the PC80 then had the similar connector. One or two of the pins were slightly different. The labelling from them was slightly different. In particular, I think there was one for B08, which was to do with that slot 8, that became 0 wait state, so cards could actually request that the PCAT didn't include any memory wait states. Then there was the 16-bit connector, which had the C and the D, and you can sort of see on here, this would be the extra data bus 8 to 15 and various other address signals, and the extra interrupts and DMA numbers that were supported on the 16-bit PCAT. Then the compact Despro 386, again, similarly had these signals defined. Again, the labels on them are slightly different. There's a few things to do with grab, which is to do with bus mastering control and things. But again, the compact Despro 386 defined these as well. And this is the schematic diagram from Despro 386. It again shows the 8-bit side of things and the 16-bit side of things we're not going to need to worry about for the moment. And then there is actually an Intel ISA bus specification. So the dates of those schematics were around, 84 to 86. Then in 1989, Intel published this ISA bus specification, and this basically just formalized the pin signals and included some timing information on pull-ups and all that sort of stuff. And so you'll see here that some of the signal names again have changed slightly. So when we go through things, I will try and sort of cross-reference these different names. And you can see here, these are the D and the C for the 16-bit connections here. So in fact, the 8-bit has 31 pins on each side, and the 16-bit has 18 pins on each side. And then just to make sure that we actually get things on the right side, so when you're looking at the top of the connector, then the A side is actually on the component side, and the B side is on the solder side. So this allpinouts.org is where I've taken a lot of the information from. You'll see here that this has the various pinouts have all been identified and the explanations of what they are. So that, and all the various timing diagrams as well. So that's quite a useful resource for looking at this, and also combined then with the Intel document. Then what I've done is I've taken that information, put it in this spreadsheet, so you can see that I've just done the 31 A pins, the 31 B pins, and the name here includes both the name that came from this document and also the Intel document. Then here is where I've actually gone through all the pins and decided whether or not we needed to include these signals or not. So in some cases, for example, we will just actually have the pin pulled high, for example, with 4.7K. Got the data bus. Again, the I/O channel ready. If we need to include wait states, then we could use the I/O ready wait functions on the PLDs for the ready wait timing, the speaker timing. The address enable is related to when the DMA has actually got control of the bus, so we don't actually need to worry about that, so we can just pull that low. So when it's low, then the CPU has access to the bus. We've got all of the address signals, ground, reset, active high. We just need to be careful that one doesn't have any interference on it. These other connections are not connected in actual fact. In fact, this sort of no wait states or S ready, then in fact is only applicable in 16-bit mode anyway, so we don't need to worry about that. Obviously the plus 12 volts we need to be careful about. Then we've got the various control signals, memory write, memory read, I/O write, I/O read. More of the ones not connected because these are related to DMA. Now there is a memory refresh pin. Now I'm not sure whether or not the VGA card needs this. There is this refdet refresh related pin that comes out of the timer, so if necessary we could connect that up, but to start with I'm not going to connect it and see if everything works. The ISA bus tends to work at 8 or 8.33 megahertz. Now we don't have a 50% duty cycle clock at the moment, we only have the system clock, but I don't think we'll need that. We don't need any of the interrupts or any of the other DMA related things. address latch enable we do need to ensure that we've got that, and that will also need to make sure that we don't get any stray signals on there which confuse the card that the Sergey documentation showed. And then we've got just the power lines. So you can see here that we've only got a fairly small subset of the pins we need to hook up to this. And then over here, I've just identified where we've got the various jumper settings, so J1 to J6, and whether they're open and closed. So basically, we don't have jumper 1 because we've already got 512k of RAM. We're having non-interlace to start with, and we're setting all of the jumpers to 8-bit mode, so you don't have to worry about the extra 36 16-bit pins. Okay, so I'm just going to plug everything in. I'm just going to take the card out first just to make things a bit easier. Just going to put the power connector in, just have to make sure the leads are the right way around. So because of the orientation of this, it's a little bit unusual. So now on this side, I've just got a couple of pull-up resistors we need to worry about. And this one's actually pulled to ground. This one's used to tell the ISA VGA card whether or not DMA is accessing the system, but we're always tying that to ground because DMA is disabled on this one. I'm just going to do the pins on the other side. Address latch enable, we're going to disable, just going to tie it to 5 volts, which is what Sergey Kiselev did, just to avoid any problems with that. Okay, so now we just need to wire in the various data and address bus signals. So the IO read, IO write here doesn't quite fit go over here, so what I'm just going to do is to wire this in down the bottom here. And then we're going to put some wires up to the various signals up here. There, read. Then we've got the lower address lines here. Let's go from A0 up to here. Make sure you've got purple is pin A0. Then we've got A8 up to A15. This carries on, and then we've got A16 to A19. Just go slot in there. Now we do need the positive going reset, so I have got a positive reset over the other side of the IO card here, and this I know to be clean, so I'm just going to plug that in here. And then this is the 12-volt line coming from my second bench power supply. Still on 12 volts and about 100 milliamps, so if everything's plugged in incorrectly, then hopefully it shouldn't do too much damage. And the plus 12 volts is beside the ground there. That's just a few leftover cables from here. So what we need to do now is to plug the VGA card in, plug in our VGA video capture device, and we should be ready to try that out. So I've plugged this in. I tried to power it up and to see if I could get any video on the screen, and I've had a few problems, so I'm just going to summarize where I've got to so far. So here's some logic analyzer output of looking at the accesses to the card, and in fact there was a couple of memory locations here when I actually compared the BIOS that I've got a dump of the version of the BIOS, the C4.4 BIOS. I managed to find out somebody had already downloaded the ROM for that, so I was able to compare the two ROMs. So what I did is, this is the ROM on the left hand side that actually come from a dump of it from online, and this is actually an S record dump of the ROM. So I basically just went into the monitor and dumped the C000 all the way up to C7FFF, and then converted it using the S-Record utility into the binary file, and I compared it. And you can see here that there are a couple of differences, and this was obviously going to cause some of the problems. And then there's another difference down the bottom. So we had about 4 bytes here that were coming out incorrectly. Now, I have done some further investigation and I've added wait states and things to the ROM access because I realised that the ROMs from 30 years ago were quite a bit slower than the ones I'm actually using on the rest of the board, so we might need to add some wait states. So, to cut a long story short, I've spent a number of days now trying to get this working, and the primary issue with it is you can't get the BIOS to scan the ROM and calculate the checksum so that it actually is happy to run the BIOS, and once or twice when it has managed to do that, then halfway through loading the BIOS, then the reading the ROM has actually gone astray. So I'm still looking into how to do that, but what I have managed to do is I've downloaded the ROM content successfully in the S-Record format and compared it with this. And what I have been able to do is to power up the Breadboard PC and load the BIOS actually into lower memory. Now, one of the things that computers did in the early years is because the EPROMs or the ROMs were so slow, in a lot of the computers around sort of the late 80s, early 90s would actually use shadow BIOS, and what they would do is copy the ROM code into another area of memory and then actually use the memory, and particularly on the 386 upwards, the memory accesses could be almost an order of magnitude faster than the accessing of the ROM, and so the Compact Desk Pro in particular would actually shadow the ROM contents. What this means is the ROM is actually capable of being moved into RAM and it will automatically relocate various references and things. So what I've done is I've downloaded the S-Record file into the memory, and what I'm just going to do now is to show you accessing the video card. I've also got a version of the test program that I had for the CGA testing. This is VGA Test 1. So it's based on one of the CGA test programs I had, and the only thing I've done here, it still shows the test information on the LED display, but it does the test pattern and doesn't do any other configuration. So it doesn't touch the palette registers, the CRTC registers, just outputs a test pattern, and it puts it to the B8000 range, which is the standard VGA, CGA sort of text display area. So what I'm going to do is to turn on the Breadboard PC. Just about see the display there down the bottom. I will speed some of this up because loading the S-Record file, it's a 32K S-Record file, it will take a couple of minutes. So when we load this, I will actually speed it up. So all we're going to do is to go in on the keypad and put in the extra segment. We're going to load the BIOS at 6000, code segment at 600 as well, so that when we have actually got it. So if we then go back to our screen here, we just need to send out the S-Record file of our TVGA 9000 C4.4 BIOS. So we're just going to load this, and once it's saved, then we will then load our test program as well. I'm going to load, send, and I will speed this up. Okay, so that's finished. Get an F on the keypad, get an E on the LED display if there has been a problem. See the F there down the bottom right hand side. So now I'm going to load the test program. So we need to set the extra segment 5000, code segment. Going to load again VGA Test 1, and that's finished. Okay, so now I'm in a position to be able to load the BIOS. So what I will do is I'll put this on full screen and you'll just be able to see that there's a BIOS power up message, and then it will go to a blank screen with a flashing cursor, and then I'll switch back and we will run the test program. Just want to set our code segment back to where we load the BIOS. Now it just so happens that the place where the BIOS actually starts, the VGA BIOS, is actually at the third byte. The third byte in the file, if we just have a look at the... So if you look at the first byte, that's the 55AA. This byte here is then the number of 512K blocks that the BIOS is, so it's a 32K BIOS. Then this next byte is actually in fact a short jump, and this is the offset. So this basically says jump further on into the code over some of the strings and things at the beginning. So in fact, if we actually want to run this, all we need to do is to type go 000 and then 3. So I'm just going to switch on to the VGA capture. Okay, so just going to type go 0003. Hopefully you can see the Trident VGA startup there. So I've taken a screen capture of the message that came up when the video BIOS initializes. So you can see it's the Trident TVGA BIOS version C4.4. It's got 512K of video memory. It's actually using 16-bit dynamic RAM bus, so this is on the card. It isn't the ISA bus, because we're only using 8-bit, so we've only got the 8-bit bus connected, and it's in VGA mode. This can also show various other things like MDA, CGA, etc. And we can see the copyright notice here from Trident Microsystems and also from Quadtel Corp. And if we just have a look at the video BIOS, so this is the video BIOS I was able to download, which is also the same as the one I've been able to transfer from S-Record. You can see that we've got the BIOS version here, C4.4, we've got the copyright messages, we've got the VGA and the various dynamic RAM modes. So this appears to be working okay. Now we've got a flashing cursor at the top here. Now I'm just going to change the code segment to 5000 where we have our test program. I'm just now going to run that. Got test 1 running on here. And now this is actually showing us our test pattern with 25 lines, 80 columns across, and then we've got all of the various colors and the flashing blinking as well. So you can see we've managed to get the VGA card working. The problem with the ROM being initialized from the BIOS I'm going to look into. I've tried adding wait states and various other things, but that doesn't seem to have made any difference. It might actually be down to problem actually with the card itself. But I'm going to have another look at that and see if I can actually get it to boot into the BIOS properly. But what this indicates here is that with the correct code running in memory, even if it's kind of in shadow RAM, we can start up and run the video BIOS, and our test program indicates that at least the video hardware is working properly. So in the next video, I'll be looking at trying to get this working properly with the BIOS. If you don't want to miss out on future videos, then please hit subscribe, and if you could hit like, just helps to make the videos available to more people. Thanks for watching.